Morning, folks. Sorry I'm a little late.
Morning.
Ah, Isaac, good to see you here. Um, so this week on the Casper stuff, um, I haven't made a lot of progress. I mean, I know that we do have the fairness constraints put into the protocol and that they're testing now, but I haven't heard much. Um, I'll find out in about an hour as to what the results have been. Uh, Mostly this week I've been writing up the negation part of the proof theory for Ladle. So I've been writing out. I've been looking at the case where you have a single-sided sequence and a two-sided sequence, and writing up what the negation construction looks like. Want to make sure that it's not too substitution oriented. There's a yeah, there's a reason for that. It needs to be symmetric. So there's some tricks there, but one thing you can think of is that you've got if K is the constructor that's on the left hand side of a rewrite rule, um, then you can form a series of contexts that have that's missing the a term. So it's got the R, but it's missing a term, and so it's frozen in that way. And there are two ways to freeze something. One is to freeze something um, by not providing the R, and the other is to freeze something by not providing both parts of the reduction, the left hand side of the rule. So then writing that up, making that crisp. That's kind of it on in terms of the development on the Casper side. Any other updates from folks? Any questions?
May I ask about what you're talking about, like proving the execution of rolling? How can we, without replaying, how can we know? We need to execute all the primitive functions. How can we know if something is inside the continuation? How can we know what exactly is the inputs for this execution?
So what's the context for your question? Are you asking about cost accounting, or what is your question?
My question is related to something that you talked about last time about proving the execution. So maybe it's not the right subject.
So no, it's fine. So I'm talking about an arbitrary rewrite system, not just Rolang. And in particular, let's look before we look at Rolang. Let's just look at row calculus, which is simpler than Rolang in certain respects. So the left-hand side of that rule is a full comprehension together with an output. So the form of the rule that we use for the proof theory is that it has to have a catalyst present. So in this case, since we're just talking about the purest form of this thing, we're saying that it's going to be the catalyst par the for comprehension par the output. So the question is, how could you suspend that rewrite rule so it couldn't go forward? So there are essentially two ways. One is you don't supply the R, and the other is you don't supply either the for comprehension or the output. Those are the so one is you don't supply a term, the other is you don't supply the catalyst. And when you don't supply the catalyst, we call that a tensor. If you don't supply the term, that's when we have a negation, because you're missing, you're suspended because you're missing a term. So essentially the difference between a tensor and something that would be related to negation. So I should be careful to say it's related to negation, right? It's an arrow type, right? So so the thing that the whole that is is marked by the negation of the thing of the type of the term that you want, because it's the contravariant version, right? It's like you mark that you need something of that type. So that's the way it's related to negation. So if you think about it like a lambda term, right? It's frozen like a lambda term. It needs something of type. If it produces something of type B, and it needs something of type A to produce that B, right? Then essentially it's you need the negation of A to produce B, right? Or you need an A to produce B, and therefore it's like the usual logic rule that A implies B, or A arrow B is the same as not A or B.
Mm-hmm.
So that's how the two are related. So we're not asking that we don't. We're not asking that we know everything about the term. We just need to know its type, in order to safely plug it into that hole.
I see. And if we have this, I see this lambda inside some continuation that we want to check. So we don't have to know exact values for input to this function. We only need to check the type.
That's correct. You only need to know that. You only need to know that you've got a term that will do the right thing.
I see. I'm just imagining that maybe I will have a function that I only expect some range on the output. So I will know the type.
This is not about output values. It's a different. It's constraining the system in a different way. It's not. Don't think of this functionally. You have to think of this, in terms of the rewrite rules, because the rewrite rules may not implement something functional. They may not even be confluent.
I see.
So if they're not confluent, we're not talking about functions. We're literally just saying that, there's in order to think about it this way, the rewrite rule says I need, a term T1 and I need a term T2 before I can rewrite to some term T3, right? And if I withhold either a T1 or a T2, then I need something like that in order to fill that hole to do the rewrite. So we're only doing it up to the details required by the rewrite rule and nothing else.
I see. I see. And we can do this checking for any nested rewrite rules.
That's right. You can do it for any interactive rewrite rules. So the rewrite rules are, they don't, like in the case of SKI or in the case of the row combinators, you may have more than one rewrite rule, right? In the case of lambda and pi and rho, you have essentially one rewrite rule that has no um, hypothesis, right? So the COM rule or the beta reduction are the only rules that have no hypothesis. The other rules are essentially telling you how things. The hypotheses tell you what context you're in, and then the rewrite rule says that you can rewrite in that context. So if we're not talking about rewriting in a context, we're just talking about, sort of the undecorated rewrite rule, then lambda, pi, rho, they all have essentially just one rewrite rule. But in the case of the SKI combinators, or in the case of the rho combinators, they have multiple rewrite rules. And so for each kind of interactive rewrite rule, you're going to get this construction.
I see.
Yeah.
Thank you.
Yeah, sure. No, thank you for your question.
Can I also ask, does it make sense to see this work with ZK snarks, like proof of execution? Can I somehow relate this, or?
So can you restate your question? You cut out for just 1 second.
I'm reading about ZK snarks proof of execution. So, does it make sense to compare these two things, or?
Oh, to ZK snarks. That's an interesting question. Let me think about that. I think there is a relationship. Yeah, I think that there is a relationship.
They heavily talk about.
Yeah. That's a very interesting point. It's a very interesting point. I'm not gonna say that I really have a handle on that yet. I don't know. I think ZK snarks have more information about values than we do, but
this is why I'm asking for the values, because they're talking about the range of some output of the function. So
but ZK snarks are mostly aimed at functions. They're functionally oriented. Yeah, I have to think about this. It's a very interesting question. It's a very interesting question. Yeah, let me give that a thought. There might be something. There might be something there that's. There might be a connection there that's worth investigating. Yeah, thank you for suggesting that.
Thank you for answering.
Interesting one. Any other questions or comments? All right. Well, some of us.
May I ask another question?
Yeah, sure. Go ahead.
Sorry. You mentioned work from Dana Scott about stochastic lambda calculus. So, and you said that there is some current research related to that. So,
no, I don't think Scott. I don't think I mentioned that Scott did stochastic lambda. There are. I mean, there's stochastic pi, and that was developed by Cardelli and Madare, so Radu Madare. Cardelli and Radu Madare did an account of stochastic pi, and then it was originally done by Rudy Shapiro and Bill Silverman to be able to model, chemical and biochemical behavior. A stochastic lambda, there's probabilistic lambda, and I can't remember who did that work, Scott, I don't know that Dana Scott did anything in that area, or at least not to the best of my knowledge.
I was watching. I can share a link where I was watching one presentation.
Okay. All right. Yeah. Please do. If I said Scott, then you know, I must have had some reason for it.
Yeah. I'm not sure, but I remember something like that. That something is currently in research and it's still unknown. So I was just wondering about that.
Yeah. Well, I mean, there's lots of work on stochasticity and these kinds of rewrite systems. They're very useful. I mean, if you're trying to ask whether or not this particular approach will handle stochasticity, that's also a good question. I don't know. I'd have to think about it a lot. Depends
I
on your
think you
model.
mentioned.
It depends on your model. So that's a very interesting question. Yes, you're right. That's a good question because there are so Martha Kwiatkowski did some good work on stochastic CSS or CCS and a corresponding logic for stochastic PCS. And so the question is, can we use ladle to generate, like if the calculus is stochastic, is the logic stochastic? So that's a very interesting question. And one of the reasons why I've wanted to make sure that the distribution law will support not just set-like things, but distribution things. So the question is there a notion of distribution that is set-like enough that we get a distributive law? And that's not immediately obvious. It seems reasonable because it extends to multi-sets. But going from multi-sets to distributions is, it's not immediately clear how to generalize in such a way that you get a monad. So there's such a thing as the Geary monad, and how the Geary monad is related to, the monadic presentation of multi-sets is not immediately obvious, and so it's not clear whether or not you get a distributive law. If you get a distributive law, then you're a good portion of the way there. But the other side of it is, there's stochasticity in the collections, and there's stochasticity in the rewrite rules. And I don't know how the stochasticity in the rewrite rules would then, line up in this proof theory kind of thing. So that's a very interesting question what you're asking there. I don't know. I'd have to go look. It's taking me
Thanks for
it's taking me a long time just to get to this point, just to understand how all the pieces fit together. It's embarrassing because it's really obvious in hindsight.
Yeah, that's usually like that.
Yeah. Um, okay. And those are great questions, all of them. Any questions from anyone else? Comments, thoughts? Going once, twice. All right. I will. We'll leave it here for today, and we'll um, see you guys next week.
Thank you.
Thank you. Ciao, ciao.
Bye-bye.